Hey everyone, and welcome to this explainer. Today, we're embarking on a totally mind-bending visual journey to understand exactly how a star collapses into a black hole. We're actually going to be breaking down the brilliant concept showcased in a phenomenal YouTube explainer by Science Click English. We're going to take their incredible visualizations of space-time and distill those ideas to figure out what actually happens in the final terrifying milliseconds of a massive star's life. Okay, let's jump right in.
So, what does the birth of a black hole actually look like? It's a fascinating question. I mean, we've all heard of black holes, right? But to truly picture this extreme cosmic event, to really see it in our mind's eye, we first need to quickly dismantle basically everything we think we know about gravity. Because as you'll see, the birth of a black hole isn't just about matter crushing together. It's about the very fabric of reality warping completely beyond recognition.
Okay, so up until the 19th century, Isaac Newton essentially told us that gravity was a pulling force, like an invisible tether connecting objects. But then, at the dawn of the 20th century, Einstein's paradigm shift completely flipped the script. He revealed that gravity is actually a curvature in the very fabric of space and time. Objects, like planets or even light rays, aren't actually being pulled at all. They're simply following straight lines along a curved spacetime.
And here's the crazy part. Just 4 years after Einstein published this, Arthur Eddington actually proved him right during a solar eclipse expedition. Eddington measured the positions of distant stars and found that their light was slightly deflected as it passed near our sun. Crucially, it was deflected twice as strongly as Newton's old theory would have predicted. This phenomenon, where the image of stars gets shifted due to curved spacetime, is called gravitational lensing. Keep this in your back pocket because it's absolutely crucial to everything we're about to see.
All right, to really see this lensing effect in action, we need some seriously intense gravity. So let's try a wild thought experiment together. What if we took our sun, kept its mass exactly the same, but escalated its surface gravity by physically shrinking its size? We're going to compress the sun step by step and watch exactly what happens to the space around it. So imagine we compress the sun, say up to 500 times. The optical distortion becomes dramatically clear. It's like looking through a cosmic funhouse mirror. At this level of density, the light from background stars is so heavily deflected that it literally bends right over and under our compressed sun to reach our eyes. And because of this extreme detour, some of those distant background stars actually appear completely duplicated in the sky. No way, right?
Now, what if we push that compression to 10,000 times? At this extreme density, the entire sky appears split into two regions by what we call an Einstein ring. And this is wild. This ring contains copies of literally all the stars in the universe. The space-time is so severely curved here that light does a full loop, allowing us to even see stars that are located directly behind us.
Okay, let's push it 15 times further. At this density, the sunlight itself is actually struggling to reach us. The light waves are stretched out so severely by the intense gravity that the star's color shifts entirely towards red. And because light can now leave the surface towards the back of the star and curve all the way around toward us, the optical distortion means we could see its north pole, its south pole, and its far side all at the exact same time.
And wow, here is the ultimate breaking point. If our sun shrank 230,000 times until it was a sphere just 6 kilometers wide, it would become completely invisible. Its gravity would be so impossibly great that light could no longer escape its surface. We'd just see a black disk surrounded by a wildly distorted sky with an infinite number of repeated, revolving starry images just accumulating around a central shadow.
So what's actually happening here? Well, the crucial point is that the space-time curvature is now so intense that the star can no longer remain static. In this bubble-like region, the star's surface would literally have to move faster than the speed of light just to resist collapsing inward. And since that's physically impossible, an event horizon is formed. Nothing, not even light, can escape. A black hole is born.
And down at the very center of this newly formed black hole, well, all of that star's matter inevitably slides down this extreme space-time funnel. It all condenses into a singularity, a microscopic region where mass is basically crushed to infinite density. It's a concept that our current scientific models still deeply struggle to fully describe.
Now, I should point out, this brilliantly illustrates reality, but our own sun doesn't actually have the mass to do this. It'll harmlessly become a white dwarf, stabilized by the collision of electrons. A more massive star becomes a neutron star, stabilized by colliding neutrons. But a star 20 times more massive than our sun, after it explodes, absolutely nothing can halt its collapse. It'll inevitably turn entirely into a black hole in mere milliseconds.
To really grasp exactly what we would see during those final, terrifying milliseconds of that massive star's life, we actually looked to the 1939 Oppenheimer-Snyder model. They studied this effect by proposing a really simple but elegant model, basically simulating a homogeneous ball of matter, collapsing inward on itself in a constant state of freefall.
And watching this model play out visually is just wild. First, the star shrinks kind of gradually, but as gravity spikes, the contraction aggressively accelerates. The surface is falling inward at an increasing fraction of the speed of light. And because the center of the star is moving away from us the fastest, and because it's physically closest to us so there's less delay in the light reaching our eyes, the center of the star rapidly reddens way before the edges do.
Then, we hit the final millisecond. In a literal blink of an eye, the collapsing star's image violently unfolds. Due to that extreme lensing we talked about earlier, its rear side becomes entirely visible to us. Then, the whole evolution appears to suddenly slow down and freeze. The star shrinks to a tiny sliver of light, completely eclipses itself, and finally just fades away into a dark shadow. Actually, wait, here is a detail from the physics of this collapse that will literally melt your brain. Because the light rays bend outwards, but have increasing trouble escaping, the black hole's horizon actually emerges from the center of the star before the physical collapse of the surface is even finished. This horizon is formed by light rays that are stationed at a fixed altitude, struggling against gravity, just forever trapped in place.
And once the black hole is formed, it just keeps messing with our visual reality. Say we were to throw a transparent object into this newly formed black hole. The object's own gravitational influence would create a secondary lensing effect. It actually dilates the image of the black hole behind it, acting almost like a cosmic magnifying glass as it falls.
But here's the kicker. Because time and light stretch out so infinitely right at the boundary, to us, the outside observers, that falling object never actually seems to cross the line. It simply appears to freeze, darken, and flatten out forever. It becomes a permanent part of the black hole's growing shadow. The shadow itself is literally just formed by the flattened images of all the objects it has ever captured.
Which, brings us to this final kind of haunting question. We know what the math says about the microscopic singularity inside, but visually, our universe firmly prevents us from ever witnessing it. So if the flattened images of everything a black hole consumes are forever frozen on its shadow from our perspective, what is the true, hidden reality happening beyond the veil of the event horizon? It's a profound limit to our cosmic perception, and honestly, a perfect place to wrap up today's explainer on the incredible, mind-bending birth of black holes. Thanks for joining me.